All right, welcome. Today we've got a really fun chemistry puzzle to solve together. We're on the hunt for a very specific number, a bond order of 2.5, and we're going to figure out exactly which group of molecules fits the bill. Okay, so let's get right into it. Here's our challenge for today. We've got these four options, and our mission is to find the one group where every single molecule has a bond order of exactly 2.5. This is what we're going to crack in this explainer. But hang on, before we can start our investigation, we've got to know what we're looking for, right? So what in the world is bond order anyway?
To put it simply, it's just a way to measure how many chemical bonds are holding two atoms together. And the formula to find it, it's beautifully simple. It's 1/2 of the bonding electrons minus the antibonding electrons. You can think of it like this. Bonding electrons are the glue holding the atoms together, while antibonding electrons are literally trying to push them apart. So when you subtract the push from the pull, you get the real strength of the bond. This little equation is going to be our key to everything.
So why do we even care about this number? Well, because bond order tells us about real physical things. As you can see here, a higher bond order usually means the bond is way stronger, which pulls the atoms closer together, making the bond shorter. It's actually a super powerful way to predict how stable a molecule is. Okay, so we know our target, and we know what it means. Now we need a plan, right? A blueprint for how we're going to solve this for every single one of our candidates. And here it is, our simple three-step method. It's really straightforward. First, we just count up the total valence electrons. You know, the outer shell electrons doing all the work. Second, we take those electrons and pop them into a molecular orbital diagram. This just sorts them into our bonding and antibonding buckets. That's what gives us the two numbers we need for our formula. And finally, step 3, we just plug those numbers in and get our answer. So let's put this plan into action. Now for the fun part, the investigation. Let's start analyzing our candidates. We're going to be methodical about this and start with the very first group, option A. All right, let's run the numbers for option A. First up, dinitrogen 2-. It's got 16 electrons. We do the math, and we get a bond order of 2.0. That's not a match. Okay, next up, peroxide. It's got 18 electrons, giving us a bond order of just 1.0. And finally, carbon monoxide. That one comes in with a really strong bond order of 3.0. So yeah, none of these hit our target of 2.5. So the conclusion here is pretty obvious, right? Option A is definitely incorrect. Not a single molecule in this group fits what we're looking for, so we can cross it off our list and keep it moving. Now, we can actually speed things up a little. Let's take a quick look at option C. The very first molecule, C2-2-, has a bond order of 3.0. So that's not 2.5, which means the whole group is out. We don't even need to check the rest. It's the same story for option D. The cyanide ion, Cn-, also has a bond order of 3.0. So another one bites the dust. Easy. So, through our process of elimination, that leaves us with just one single possibility. You see where this is headed, don't you? And now, it is time for the big reveal. Let's see if option B holds the solution to our puzzle and gives us that magic number of 2.5 for all three molecules. And there it is. Let's just double check the numbers. The N2+ ion has 13 electrons, run it through the formula, and yes, we get a bond order of 2.5. It's a perfect match. Next, the O2+ ion. It's got 15 electrons, and what do you know? It's also 2.5. And finally, nitric oxide, NO, which also has 15 electrons. You guessed it, a bond order of 2.5. Every single one of them is a hit. And there you have it. Every single molecule in this group fits our criteria perfectly. We have found our winner. The correct answer is option B. Puzzle solved. So that wraps up our investigation, but here's a little something extra to think about. Those same molecular orbital diagrams we use to find the bond order, they can also predict a molecule's magnetic properties. So how do you think those unpaired electrons in the diagrams might affect whether or not a molecule is attracted to a magnet? That's a good one to chew on.